Hello, I'm Mike McCulloch. Today I'd like to talk to you about the faint young sun paradox, which is something that was noticed and first published in a paper by Carl Sagan and George Mullen back in 1972. And they noticed that according to the standard model of the sun, how we understand the sun works, which is admittedly not necessarily correct, that when the solar system was forming 4.6 billion years ago, the sun was likely to be 30% dimmer. This is because it's brighter now, because with fusion occurring in the sun, the particles, the mass that produce the pressure, are slowly being converted to electromagnetic radiation and light that can escape. So the pressure supporting the sun is going down, so the gravitational force is slowly winning the balance and compressing the sun, making it hotter. So in the past, it was likely to be cooler. So Sagan and Mullen proposed as a solution that there was more ammonia in the atmosphere back then, but this has since been shown to be unlikely because ammonia is unstable. And it's also been argued more recently that there could have been a lot more carbon dioxide in the atmosphere back then, which could have produced a greenhouse effect that's counteracting the faint young sun. But they need about 10% carbon dioxide to do that. Carbon dioxide is a greenhouse gas, of course. This also applies to Mars, which 4 billion years ago or so seems to have had oceans on it, which also is not compatible with a dimmer early sun. So quantized inertia might provide a solution to this, because in quantized inertia the value of the gravitational constant is, well, not constant. So in QI, g is given by c squared theta, so speed of light squared times the cosmic diameter squared, divided by 2 times the mass of the universe. And we can simplify this still further, because in quantized inertia also mass is proportional to, almost equal to area. So we can replace this with something like c squared over theta. G is c squared over theta, barring a few small factors. So that means that 4.6 billion years ago, or maybe 4 billion years ago, we can work out the value of g, because we can work out what size the cosmos was back then, which would reduce the size of theta, and so would boost, according to this formula, it would boost the value of g. And we can work this out, and we can work out that g was about 1/3 greater back then. So that's interesting. That would have all sorts of effects for the sun and for the solar system as well. It would change the orbits of the planets. It would change the amount of fusion occurring in the sun, because the compression of the star would be greater. And in fact, according to the standard model of the sun, the luminosity of it is proportional to g to the power 7. So a very small increase in g would mean a massive increase in the luminosity. And in fact, if you have back then an increase of g of 1/3, it would lead to a 6-fold increase in the luminosity of the sun. So that's very significant. But that's not the only thing that would happen. And I'm assuming here that the speed of light is constant over this time, but I'm not even sure about that. It might vary as well, which would have implications for fusion. But what this means is that it's very likely that the sun was far more luminous than expected back then. And this would solve the faint young sun paradox. Okay, so I hope you've enjoyed this short, and please leave any comments. And yeah, please do subscribe to my Patreon channel and become a member on this channel. on Patreon, you'll have access to about 300 articles that I've already put there that are interesting to read, I promise you. And I look forward to seeing you next time. Goodbye.